Hey guys, welcome to our first pre-learning session. So you should at this point have the Unit 0 notes packet printed, or you've made a digital copy of it in Google Drive. We are going to talk through the first 3 sections of this, and you're going to take notes. We have a couple of little video clips that you're going to see as well. And really, Unit 0 is kind of an intro unit. It's also an opportunity for us to remind ourselves about some qualities and characteristics of scientific thinking, as well as data collection, graphing, and running some calculations on our data that then let us sort of speak intelligently about that. So here goes our first session of notes. All right, so I am thinking that at some point in your time as a student in science class, you have learned about something called the scientific method. I prefer to think of it as scientific thinking because it's a pretty logical thought process as opposed to something that is very scripted and directed and you must follow these specific steps. It's more of a natural process. And so either way, you've learned about it before, or as we talk about it today, we're going to start with something called a hypothesis. A hypothesis really just comes from an observation, a question, a curiosity, something that you have noticed in the natural world. So for example, as I sit right here recording this video, there is a plant in one corner of the room that I'm in that is doing really well. It's very vibrant, it's grown, its leaves are green. And then there is another plant in a different place in this room that is looking kind of sickly. It's not looking so good. And so I might observe that and I might wonder, why is one plant growing better than the other? That leads me towards a logical thinking process. So hypotheses are based on just everyday observations, questions, curiosities, noticings that you have about our natural world. Now, I'm thinking that a lot of you probably have been taught that there is a specific way that you write a hypothesis statement. So if you have ever learned that you must write a hypothesis as an if this happens, then this will also happen statement, I'm going to loosen that up a little bit for you this year. Hypothesis statements do not have to be written as an if-then statement, but they do have to follow some basic guidelines. So let's talk about what must be in a hypothesis, or what are the must characteristics of a hypothesis. The first thing is that your hypothesis has to be somewhat of a logical, educated guess. So I might be thinking, if we're sticking with the plant example in my room, I might be thinking, that plant that's looking like it's growing well, it's really close to a window and it gets a lot more sun than the plant that's on the other side of the room. Maybe the sunlight is the reason that the plant is growing well. That's a logical, educated guess that explains my observation. I would not want to put forward a hypothesis that says, maybe that plant is growing well because at night, magical plant fairies come and sprinkle it with dust. It's probably not a logical, educated guess that explains my observation. A hypothesis also must be something that's testable, which means you have to be able to generate a test to see if what you're thinking is true or not. I can test the effect of sunlight on a plant. It's going to be kind of hard to test if magical fairies are coming into my house at night and making my plants grow. The last thing that a hypothesis must include is a prediction between the relationship between two variables. And we'll get into this in a minute. These variables are called the independent and dependent variable, but a hypothesis must state what you think the relationship between those two variables is going to be. So here's an example. As As a plant's exposure to UV light increases, so does the height of the plant. This hypothesis identifies two variables. Those variables would be light and height, and it predicts a relationship between them. So if you're visual, here's that relationship. As light increases, so does height. So light and height were our variables. As one of them goes up, the other responds by going up as well. That is a quality hypothesis statement. Did not have to be written as an if-then statement, but did have to follow those three things that we talked about. Now, a hypothesis will lead us into designing a controlled experiment. Now, controlled experiments, you probably remember a little bit about those. We're going to watch a quick video together. All you have to do is keep watching the screen, and I will play it for us. It reviews experimental design. Here we go. It's right in the middle. Let me back up that video. Ooh, get back here.
These measurements are your data. Is getting fertile.
Whoop, all the way back. Okay.
Maybe you have an idea that you think might explain a situation. This is called a scientific hypothesis. How could you find out if your hypothesis is correct? Well, you'd set up a controlled experiment in which you control or keep constant all the factors known as variables, except for the one you want to test. Let's design a controlled experiment to test a fertilizer which claims it makes plants grow bigger, lusher, and perhaps produce more flowers, fruit, or vegetables. If you wanted to see if the fertilizer works, how would you set up a controlled experiment to test this claim? First, you would get two plants of the same species. Let's call them plant A and plant B. Everything about the plants should be exactly the same, including their size, health, and age. Next, you would put each plant in identical pots with the same amount of the same kind of dirt or soil. You would water them both the same amount at the same times. You would also put the plants next to each other in the same place, such as a windowsill, so that they're both exposed to the same amount of sunlight and kept at the same temperature. It's important that everything is the same, because the purpose of your experiment is to find out whether or not the fertilizer works. So, what would be different? In this experiment, the only difference is that only plant A would get the fertilizer. Now remember, your hypothesis is that plant A, which is getting fertilizer, will grow bigger compared to plant B, which isn't getting any fertilizer. How would you know whether your hypothesis is correct? You'd know because you'd regularly measure the plants during the course of the experiment. For example, once a week for a period of 3 months. You would record these measurements throughout the experiment. These measurements are your data. At the end of the experiment, you would look at your data and compare the measurements of plant A, which got fertilizer, to plant B, which didn't get fertilizer. As you can see, plant A did grow bigger than plant B, so it appears that the results of this controlled experiment support your hypothesis. So let's recap the elements of experimental design. What were you testing? You were testing to see whether or not fertilizer promotes plant growth. What was your hypothesis? The hypothesis was that the plant that got fertilizer would get bigger than the plant that didn't get fertilizer. What were you measuring? You measured the growth of both plants. How do you know if the results of the experiment support your hypothesis? Well, if your hypothesis is true, you would have seen that the plant that got the fertilizer actually did get bigger than the plant that didn't get any fertilizer.
All right, so let's go back into our PowerPoint and let's talk about these elements to a controlled experiment. So in the video, we saw that there are different kinds of things that we are manipulating, variables that we're manipulating. The first variable is called the independent variable. And the IV, that's shorthand for independent variable, the IV is what you are changing on purpose. It's usually the focus of the experiment. Now, in the video that we just saw, the independent variable was the fertilizer. That's really what the experiment was testing. Does the fertilizer affect the plant growth? So the independent variable was fertilizer. You only want to manipulate one independent variable at a time for a purpose that we'll see in just a second. Another variable that we saw in the experiment was the dependent variable, abbreviated DV. Now, the dependent variable is what you are measuring or collecting data on. In the experiment that we just saw, the dependent variable was the plant height. And a dependent variable is called a dependent variable because it is dependent upon the independent variable, meaning it is what is happening as a result of changing that independent variable. The more fertilizer you got, the taller the plant grew. The third category of variables are called CVs, and these are controlled or constant variables. So that's everything else in the experiment that was held the same across the board. So, same species of plant, same container size, same amount of soil, same amount of water, same time of day that they were watered, next to the same amount of sunlight or artificial light. All of those are controlled or constant variables. These are super, super important in an experiment. Why? If you don't have a controlled or constant variables, you cannot attribute the results, the data that you're collecting, back to the independent variable. But if you do have everything else controlled as best as possible, then you can pretty confidently say that the data that you collect is the result of whatever change you made in the independent variable because it's the only thing you changed. You kept everything else the same. Let's look at groups that exist within an experiment. So there's always the experimental group or groups. These are the groups that receive the independent variable or the independent variable is manipulated. So in our video that we just watched, the experimental group was pot A that received the fertilizer. There would also be a control group. And in the video, the control group was group B. Now, control groups are the groups that don't get the independent variable at all, or it's not fluctuated, it's not manipulated. If what you're testing is a particular amount of fertilizer, you wouldn't have it fluctuated. So usually you can identify a control because it's not receiving the independent variable. Controls are very important, again, because having that data lets us look at the results from the experimental group and attribute that back to the independent variable that we're actually testing. Control groups allow for our experiments to have more reliable results. Now, what we saw in the first video was a bit of an oversimplification of an experimental design and control group. So what I want to do is introduce you to a little bit more detailed level of thinking about controlling your experiment so that your results point back to an independent variable. So again, we're going to watch this video. All you have to do is keep your eyes on the screen, and here we go.
This is Dr. Johnson. He wants to do an experiment to learn the effect of caffeine on blood pressure, so he has decided to use coffee.
I, the brilliant and world-famous Dr. Johnson, have developed the hypothesis that caffeine increases blood pressure. Today, we will prove this hypothesis true. You have before you cups of very caffeinated coffee. Please drink 2 cups of coffee each and get your blood pressure taken. Look at all those high blood pressures. We can definitely say that caffeine increases blood pressure.
But how do you know the coffee did anything? You have no point of comparison. They might have had high blood pressure before they even started drinking coffee.
But those are very high. What else could have caused it?
Maybe they were all irritated at you for insisting on a hypothesis to frame your research, rather than asking an unbiased question. In any event, you forgot your negative control.
A negative control allows for a comparison to see if the agent under study is having an effect. Without a proper negative control, the scientist has no way of knowing if the agent is responsible for an effect that is observed. What is your negative control, Dr. Johnson?
Today, we seek to answer a question. What is the effect of caffeine on blood pressure? You people on this side of the room will drink 2 cups of coffee, and you over here will drink nothing. You see, I knew it. Caffeine increases blood pressure. You see a clear effect in comparison to the control.
But all those people drank coffee, right? How can you conclude anything about caffeine?
It's caffeinated coffee. It has caffeine in it.
Sure, but it has other things in it as well.
A negative control is more than just the unperturbed case. While the control group here helped to show that something happened, it did not prove that caffeine was the cause because there was a lot more in the coffee than that.
Okay. How about uncaffeinated coffee? Would that make you happy, Kitty?
Yes, that would be a good unperturbed by X control.
The unperturbed by X control is a negative control, where everything that the test subjects are treated with are given to the control group, except the component under study, in this case, caffeine.
Today, we will seek to answer a question. What is the effect of caffeine on blood pressure? You people on this side of the room will drink 2 cups of very caffeinated coffee. You people in the center will drink 2 cups of decaffeinated coffee. And you other people over here will drink nothing.
How about giving them water to see if it's just the fluid that's increasing the blood pressure, or just being forced to walk up to you and drink something quickly is enough to cause the effect?
Today, we will seek to answer a question. What is the effect of caffeine on blood pressure? This side of the room will drink 2 cups of caffeinated coffee. You over here will drink 2 cups of decaffeinated coffee. You folks will drink water, and you will drink nothing.
This now looks like an experiment with the appropriate negative controls. Well, you have your answer.
But there's no effect.
Exactly. Once you did a controlled experiment, you learn that the change isn't due to caffeine. People who just drank water also showed an increase. Maybe they got nervous, or maybe drinking that much fluid quickly is enough to increase blood pressure.
I was so sure caffeine would increase blood pressure.
Okay, but we now know that's not true.
But what if we make them drink 20 cups of coffee?
I see we have more work to do with you.
A proper set of negative controls is critical to determine if there is an effect in an experiment. Without an all but X control, where X is what's being studied, it's impossible to know if the component under study is causing the effect seen. In this case, in response to the question, what is the effect of caffeine on blood pressure? No effect was observed.
So that's pretty interesting when you consider how they just continued to ask, could we control that? Is that really letting us just test the caffeine? Maybe we should give them some water to see if there's anything else at play here. So the negative control just continued to sort of weed out any other possible reasons so that by the end we could really attribute, or not in this case, blood pressure back to caffeine. All right, let's move into collecting and displaying data. So in collecting data, I'm going to keep this short and simple. Your data, once collected, should be organized into a chart, and that chart should also always contain the units of measure. We'll see an example of that in just a second. Once you have collected your data, you have to visually display your data. So now we get into the graphing conversation. A good graph has lots of different elements. The first is a title and both axes, the Y and the X axes, labeled. And so I'll get into explaining that dry mix thing in just a second. Let's look at, there's my chart for point A. Notice this data has been organized into a chart, and we have captured the units of measure right here, centimeters. So make sure you always have units, even in your data chart. All right. My next image is a good graph. So quick review, you have a y-axis right here that's vertical, and you have an x-axis that is horizontal. If that ever gets confused in your head, just remember y to the sky. Y points to the sky is your vertical axis. Now, in graphing, there's a rhyme and a reason to what data goes on each axis. Your dependent variable information always goes on the y-axis, and your independent variable information always goes on the x-axis. And there's a fun little memory trick to help with that. If you can remember the word dry mix, dry dependent on the y-axis and mix independent on the x-axis. You'll get it right every time. So a good graph always has a title and its axes labeled correctly. A good graph also has units recorded on the axes as well. It is scaled appropriately, and it has a key if necessary. So let's talk about 3 and 4 for just a second. Here is a great example of a graph that has a title and its axes labeled with units, but it is not scaled appropriately. So look at, what do you think is wrong with this? It's a very large piece of graph paper with a teeny tiny little graph. So really, this person should have used the entirety or the majority of this y-axis, starting 0 here and 80 all the way up here, and also stretched out the x-axis as well, using more of that space, extrapolating that data a little bit more, and allowing us to see possible trends. And then number 4, a key if needed. This comes into play if you're doing a bar or a histogram, or if you also are doing like a double or triple line graph. So put a key in there if that is necessary. Let's talk about types of graphs. I included the pie chart, even though it is rarely seen and used in AP Bio, just so that you know a pie chart is really showing parts of a whole. So most likely this is favorite type of movie based on a survey. You're seeing what percent or what part of the entire participants that took the survey enjoyed sci-fi or drama or romance. Again, rarely used, but included just to be specific. A bar graph, we do see bar graphs. Bar graphs represent categories of data. So this is for categorical data. And here's the deal. A bar graph shows categories that really are not related to or dependent upon each other, which is why the bars don't touch each other. So here's what I mean by that. The number of people that like apples has nothing to do with or no influence on the number of people that like oranges. Those two pieces of data are not related to, connected to, or dependent upon each other. So they are physically not connected on the bar graph. That's a little bit different from our next one. This is a histogram. Now, histograms show a continuum of data. So the continuum here is height. We go from a very small tree up to a very large tree. And because height is, like a number line, a continuation of numbers in order from small to big, these data points technically are related to each other. And so they're touching each other. The bars in a histogram make physical contact with each other because this x-axis is a continuum of data. Let's look at a line graph. These are super common in AP Bio. So here are a couple of line graphs. Line graphs always represent change over time. And so time is always found down here on the x-axis. That might mean small increments of time, 1 minute, 2 minute, 3 minute, 4 minute, 5 minutes, or it might mean large chunks of time, days, weeks, months, years even. But time will always be represented on a line graph. And we connect the data points on a line graph because the time is, again, a continuum, meaning you can't get to time 4 minutes without having gone through time 1, 2, and 3. So because the 4th minute is actually a part of and connected back here to the 1st minute, we connect the data points in a line graph. That's different from our last graph, which is called a scatter plot. So a scatter plot is also very common. Scatter plots show a relationship between two variables that are seemingly unrelated, but really we graph them and we draw this line of best fit through the middle to see if there is a relationship. So this particular graph is showing data points on the length of a person's second finger compared to the length of their 4th finger. So is there a relationship between your second finger and your 4th finger? Maybe no. Graph it. Actually, I'm looking at the line of best fit and I would say yes, and we'll see why in just a second. So scatter plots, because the data isn't represented on a continuum, we don't connect individual data points, but we do draw something called a line of best fit through our data to show the trend that may or may not exist in our data. So a line of best fit, if you're not familiar with that, is a line through the data that reflects about as many data points above the line as there are below the line. So you just get your ruler and or your straight edge and you kind of angle it through the points and get about as many data points above as below, draw your line, look at your trends. When it comes to trends, here are the 3 most common: a positive correlation trend, a negative, and no correlation. So I've color coded them. This first, which this picture is in your notes, this first one is representing a positive correlation in the data, which says as one variable increases, the other also increases. The second one is representing a negative correlation, which says that actually as one variable increases, the other one goes down. And so that's an inverse relationship between the two variables. And our third in green here shows really no correlation at all. There is so much scatter in the data, you could not say that as one variable goes up, the other variable responds in a particular manner. So this brings us to the end of our notes for today. You need to make sure that you go back on the Jamboard that is posted for this particular lesson and you ask any questions that you have on that Jamboard before we meet live again next. So questions about content, questions about anything I said or any words that you saw up here or any images that you saw up here, questions about the video, anything that you want to review or that you need a little extra support in, drop it on the Jamboard and we will start with that at our next meeting. All right, guys, see you later.